Hello. 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 Nice, nice. All right.
Good afternoon.
Good afternoon. Thank you for saying so. Good afternoon to you. All right. Excellent. Thank you. Good afternoon. Oh, actually, sorry, I'm gonna ask. Who was that? I missed it. Who just said that? I just have to.
Oh, it was me.
Oh, good afternoon, Catherine. Thank you. And company. All right. Thank you. And good afternoon, David. Good afternoon, Liani. Good afternoon, Zitlali. Good afternoon, Janine. Good afternoon, Shankia. Good afternoon, Shankia's emoticon or emoji. Sorry. Hello, Avery Yeller. Good afternoon, Kirsty. Good afternoon, Aja. Good afternoon, Vince. Hello, Renice. And welcome back. Good afternoon, Hoyin. Good afternoon, Jean-Pierre. Good afternoon, Jacob. Awesome, awesome. I'm psyched. I'm actually going to turn on a light. Wait, I'm sorry. There's a lighting thing. Oh, no. Someone else is coming. Okay. Who did I just? Okay, so that's. Who else? Good afternoon, Tomika. If I didn't say, good afternoon. What else didn't I say? Oh, good afternoon. Awesome. Good afternoon, Tamika. Okay. And I think, oh, more. Oh, good afternoon, Noelia. Awesome. Thank you. Good afternoon. What else do we have? We said Tamika. I said Jacob. All right, I think. Oh, good afternoon, Juanita. And I think good afternoon. Awesome. All right. I think that's everybody who is with us now. Oh, yes. I'm sorry. Hello, Antonio. Good afternoon. Awesome. Okay. Excellent. All right. I think that's all of us. And I think that's all of us, if that makes sense. Okay. Again, this is great. I think we're all getting to know each other better and better. We're all putting up with this more and more. I am, and I got a couple of comments from you guys yesterday, like good comments. Like, again, I know that for some people this is already way too slow, and for some people it's way too fast. Like, I know that, and that's reality. I am. I don't want anybody to suffer. Things will change, and whoever you are, if you're thinking it's too slow, it might you might have a different feeling on a different day, et cetera, et cetera. Wait, more people coming. Sorry. Oh, there are a lot more people. Wait, sorry. Well, the quick thing is we are going to get faster today. I would, I mean, if you're feeling that it's already too fast, again, you can let me know. And I can tell in some of your homeworks, like some of this material is already like entering lands that are not comfortable totally for some of you. I do know that. And you letting me know is a good thing. It doesn't mean, of course, it's a class. Like, obviously, I can't totally just like stop on a dime or reorient everything all the time for any given individual because like there's more than one individual in the class. But that doesn't mean that letting me know is a bad idea. Like even if I can't immediately respond to your needs, or even if you tell me something you don't think anything can be done about, it is good for me to know where people are, and that's part of like what the homework is for and stuff. Anyway, I'm already babbling. What I'm trying to say is, and wait, sorry, more. Well, when I say that we're going to get faster and faster, the main thing I mean about that is just that hopefully a higher percentage of each day will be spent on me just like doing straight physics and solving the problems, which I think probably most of you want no matter what. Like, there'll be less of me just talking and more of me just doing the physics. That's a large part of what I mean about us getting faster and faster, sort of covering more material more densely like that. But there's still ways to cover material that can be clear and slow down for people, or, and I guess to put it bluntly, we're going to get more and more into this calculus and this math, right? I know already for a fact that some of you are already like not so comfortable with the calculus we're already doing. It's not a question of fault, and it's not a question of apologies in either direction, yours or mine. But I guess what I just want to say is, if you're already a little bit uncomfortable with where the calculus is, don't be afraid to admit it to me in private. Number one, there is no shame about that. It doesn't mean I can always give you all the points. Like, if you can't do a calculus thing on the homework, maybe you won't get like 100% on the homework, whatever. But I shouldn't even call it a percentage. But I know but letting me know is still good, because there are ways I can talk about. The more people I know need to hear more about certain things, the more I can talk about those things while I'm doing stuff, in a way that doesn't necessarily have to slow us down, or even can even help people that think they already know those things, right? So I'm just saying feedback goes in both directions, and there's no fault, no shame insurance policy. The reality is, as I've mentioned to some of you before, and I'm saying this partly because I spent a long time yesterday, and we're still not even finished with homework one. So if I were some of you, I'd be, what's the deal with this class? Like, it's been 3 days, and he's expecting us to do homework three. He's still talking about homework one. That's crazy. Some of you might be thinking that, and I respect that. Others of you might be thinking, oh my God, like it's only day three. Like, we're like, what exponential functions, like integrals, like what is he talking about? And I respect that too. I'm not, and it is what it is. Obviously, I have to do what I have to do. But any of you like pointing out to me either explicitly on the side, like this is where I'm at with the math, or just showing me in your homework, like it is sort of clear, like it just helps. It helps us all get to a place that works for everybody. And the final thing about that is just like, because I have been doing this for a long time, as you know. I mean, I've been teaching this material again for like 28 years, but specifically, let's even say this summer John Jay Physics 2 course, like even that I've been doing for like 10 years now or something like that. And I know that in this course is heavily mathematical on the one hand, but we always have a bunch of people in this class from other schools who have done calculus, who are in other majors, who might have done a lot more calculus than some of us in the room. Like, it's always true that there's a big bifurcation of backgrounds in this group. I just want you to know that I know that people have very different backgrounds. The reality is, you can do calculus like 50 times, and then on the 51st time be like, oh my God, suddenly I actually understand calculus. Like, there's a way. What I'm trying to say is, even especially for me, the more people explain fundamentals to me, the more I really understand the super sophisticated stuff that I thought I was trying to do. Or put another way, there's a way to think I understand things when I actually don't even understand the level at which I actually don't understand the thing I think I understand. And hearing it reinforced or done through fundamentals can super help. Put last one final way, someone asked me on the first day, what do I love about physics and math? And I babbled for like an hour because I love that question. But I didn't say one of the most obvious things about what I love about physics and math. And that is that all of the or maybe I sort of did, but all of the final, most advanced, most sophisticated, most contemporary truths, like the calculus 5 truths, or the physics 17 truths, or the physics that come out in the year 2021, like all those truths are contained in the early fundamental truths. Like, that's why math and physics are deductive or analytical, if you want to say, or a priori, if you want to say. They're the kinds of sciences or fields of study where one step logically follows from the step before. So the truth is, if you really, 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 really study the initial steps, which is sort of like what I spend my life doing, if you really keep re-looking at the first fundamental steps, i.e. the definitions and the laws of calculus and physics, the more you stare at those fundamentals, the more you see that they are packages that contain necessarily all the advanced stuff that is to come, like all the advanced, and that's why we believe all the advanced stuff, because it gets logically derived, deduced, inferred, implied from the early steps. So the better, so I guess I'm also saying to everybody, even if you think you've seen some of this material before, the truth is I've seen it, like I see it 5 times a day, every day for 28 years. And it doesn't bore me, because every time I look at it, what I really see is, oh my God, that leads to that. Oh my God, that's going to lead to that. Oh my God. And I understand the advanced stuff that much better. Anyway, so that's everybody. So that's a long way of saying, when I say we're going to go get faster and faster, I mean that to assure some people, but I mean it not to scare other people. What I really mean is I want to get to the material a little bit faster today. Wait, I'm going to look in the chat. I'm afraid to look in the chat because I'm afraid. Oh, are we recording? Yeah, we are recording. Okay, wait, I'm afraid to look at the chat because, oh, oh, oh. Oh, wait, actually, okay. So everything that's in the chat is, okay. All right. Everything in the chat is so relevant, to like exactly what I'm saying, that I'm going to try to do fast. All right. I'm afraid of getting myself lost in the chat, but yeah. All right. A, I do plan to get to homework 2 in the chat today. I have many things to say about homework 2, including that some people have now gotten it back. Some people have not. I'm going to address that. That is not personal to any of them. That's just me still trying to catch up with you. But yeah, we're finally going to move on to homework 2 today. We won't finish it. And yeah, so that's one question in the private chat. Number 2, definitely, if you got any kind of grade on homework 2 or homework 1, that you don't like, you can absolutely resubmit. Mostly what I hope is if you got, so homework 2 was worth 350 points, 350. If you got less than a 300 or something, I hope that I wrote in the comment or somewhere like something somewhat clear about really what was my main critique. And honestly, this is everybody now. Again, I think these are all fair questions. I'm just trying to, I want to. Anyway, these are all very fair questions. I just don't want to bore people, but definitely, first of all, on any homework ever, but especially homework 1 and homework 2, if you got less than a 300 or something like that, I mean, on this one, that hopefully I told you like what it would take to get the full score. In some cases, it's just because some people didn't get to the last part yet, but they still wanted to hand in something. Fine, absolutely a good decision. So then when they do the last part and resubmit it, they'll get the full score. Quick side note on that. If you're one of those people, like if you're handing in things in stages, that's totally cool. But the one thing I ask is like when you finally do that third part, if you haven't done it yet, that please do just like restaple it to the other first parts you did. I mean, you don't have to recopy by hand or anything, but somehow reattach it and just give me a new file that freshly contains everything. Even if you want to make sure that I know that I've already given you credit on the first part or something, you can write me a note, but whatever you give me, anything, give me a full contained, like one big document, even if there are other documents still sitting in the portal. I hope that makes sense. Like, anytime I sit down to grade something of one of yours, I want a complete, as complete a document as I can see at that stage to grade it, if that makes sense. Definitely you can resubmit homework 2 if you didn't like your score, and you'll get all the points back. Let me say also, in many cases, you might be needing to resubmit for a very simple formatting issue. Excuse me, there's one critique. There's one thing I'm asking everybody to do that's super simple. I mean, you probably don't have to do it for other classes. It may seem really annoying to you, but that is what I am asking everybody to do, is not do their answers on my typewritten sheets. Like, more people, sorry, hold on one second. Like, treat my typewritten sheets as though they're exam sheets, and then you're handing in a separate clean thing that's like as though you owned your own blue book, so to speak. That's important to me for a lot of reasons. It's a thing that I care about, and I need everybody to do it. It's partly a habit that I need you to be in by the time you actually take your exams, which are like done very much like this in many ways, and are submitted through Google Classroom. So I may have slashed off a huge amount of points if you did your homework all over my sheet, just because it's like really hard for me to read. It cuts down on the amount of work that you can show, all these reasons. But if you did all the hard work already, just transfer that work to another piece of paper, just copy it over and resubmit, and you'll get all the points back. The points are not supposed to be a punishment. They're supposed to be like a communication of how if that makes sense. So yes, definitely. If you didn't like your score on the homework, definitely just resubmit it. I will get a notification that you've done that. I will relook at it like it's a fresh thing, and I'll give all the points back with there's no lateness or anything. So I hope that's clear. And it's not supposed to be, and I apologize if you didn't like your score. It really might just mean some formatting thing like that. Okay, another thing on that, as long as we're talking about, and there's still plenty of time to hand in homework 2, even though I will start getting to it today. That just makes it maybe easier for some of you to start and get rolling. But believe me, there's still work for you to do, even if I talk about it. But on the same note as please do everything on separate sheets. Also, again, I have this tick. I know it's like a me thing. I know other professors don't ask for this, but I have this need for you. And once you get used to it, it's super easy. But until you get used to it, it seems out of nowhere. I'm saying to you guys like that I write questions out, then you take out a separate piece of paper and you don't cut and paste my questions or copy and paste my questions, don't verbatim screenshot them, but somehow, nonetheless, in your words and with your diagrams, you make the question clear back to me on each thing that you do. I am asking you to do that. That's possibly one of the more annoying things that I am asking everybody to do, and it is worth points. Let me be really clear on what that really ends up looking like in the end. What I'm really asking for all of you is when you turn in a homework thing to me, it should be a document that makes sense, that tells me physics arguments or provides physics derivations, provides physics solutions in a form that stands on its own. Like, you're really secretly part of all my methods or whatever is that I want you to create homework responses that are independently legitimate pieces of physics work. I want you to create homework physics responses that are just documents of physics, that aren't like baby contrived exercises where the only person who would understand them is the guy that's giving you a grade. Like, we're trying to use school here to practice for reality, so to speak. So don't think, so when you're doing your homework, think of it as like a little mini publication or a mini report or a mini presentation, a mini proof where, yeah, I prompted the question because I'm the one funding the research. Like, I'm a guy who wants to know when v equals 0, what's x, right? So, I mean, really, this is an analogy, of course, but that's sort of the mindset is, imagine I'm funding your research and you're an expert physicist and I want you to find out for me, given any kind of mass on a spring, when it reaches 0 velocity, like what position will it be? So your research says, like, it starts by saying, when v equals 0, determine x. And then you do a bunch of work and then you circle the answer, x equals 3 meters or whatever, and you circle it. And now you have a piece of paper that actually, especially since you started with a diagram, now anybody could come along, look at your piece of paper and see it as something that is imparting physics knowledge to the world. Like, no joke. Like, my friends who like physics but are not in this class could look at it and be like, oh, that's cool. Oh, that's a cool analysis of a mass on a spring. Oh, yeah, that makes sense. Oh, I get that. Or even, oh, wait, I think he made a mistake in step 3, or she made a mistake in step 4. Like, you want to write physics that stands on its own. Even if it was prompted by me, it is still physics thought process. And the most blunt way I can say this is write out your physics so that I can grade it without looking at anything else. And honestly, really, that's, I mean, I don't know if that puts it more crudely or if that pisses you off, like, but is the real deal. Like, even though I do know these things, I made them up, I wrote them, I look at them, but I can grade so much faster and so much better if I could just look at your work and if it just stands alone and tells me what it's trying to do and then does it. Plus, I can really see if you really get it, if you tell me what you're trying to do and then you do it, rather than just like fragmenting answers at me. Okay, this is all also the way the exams are graded. This is all practice for what we're looking for in the exams. By the time we get to an exam, you'll see, if you weren't in the class, you'll see that we like practice for the exams anyway, and they're take home anyway. So like all the answers are all over the web. Like, it's going to be an examination of, do you really understand what you're writing more than anything else? And the best way for me to know that is if you communicate the questions and the answers all as one independent package that doesn't require cross-referencing. So like, write out homework in a manner that I don't have to look at anything else to do it. Yet don't do it on the homework sheet itself, because that defeats the purpose. If I write anywhere on your homework, if I write ID, this is a new abbreviation, that means independent document. It means everything I just said. And I know I'm babbling, that's one. But these are all great questions. If I'm talking fast or intensely, it's just because I don't want to waste your time, but these are very fair questions. I also, wait, okay. Oh, yeah. Oh my God. Yeah. Wow. What a nice thing Catherine wrote. That's a really good point. I totally forget. I guess she thinks this is too slow, but okay. Yeah, that is true. That's totally true. I forgot on the YouTube channel. All the times this entire past course is already up there, and you're welcome to poke around and see the advanced. You could see the YouTubes of the old versions of this class. I forget that all the time, but be my guest, especially if this is going too slow for you. Also, but good point, Kathy. Thank you. Also, as far as the YouTube, and also one of the questions in the chat, yes, I'm trying to take your stuff seriously, all of you. I feel bad that I haven't gotten all of your homeworks back yet, but what you say in class shapes the class. That's also why I repost. That is also why I even forget that the old YouTubes are there, because I do feel like every semester is like its own class. Wait, someone's here. Sorry. So like, yeah, one of you asked if I did make more homework game portals. And I think most of you are getting how the game is working. It seems like most of you are turning them in every day. I think I've gotten back every single game term that anybody's turned in. And I appreciate that. Those are all just points there for you. But like please, like there's special portals. Don't forget. I'm not going to mention names, but like one of you handed in a game turn and mentioning things that you said yesterday, and you got 50 points for it, and that was great. But one of the things that one person said yesterday was, and many people did this, but just as an example, one person literally, when I asked like, what's the integral of I think I asked, what's the integral of 5 dt? It was either what's the integral of 5 dt or what's the integral of 5t dt. I don't remember. And one person, many people, but one person in particular wrote in the chat like 5t plus c, or 5t squared over 2 plus c, whatever the answer was. They totally wrote an answer in the chat. I'm saying, right, and they totally mentioned that in their like class participation 50-point sheet. Great. I'm saying they can also take that in addition to the 50 points. They should also put that in the portal that says for right or for wrong, because they had the guts to say something that was either right or was wrong, happened to be right. But either way, they should put it in the portal that says for right or wrong and get 75 points for having, because it also shows like that she was right there, like with what was going on at that moment. Even if she got it wrong, she should put it in that portal, like double dip, so to speak. And if we need more portals like that, I'll put them up. And that doesn't apply just to that person. There were many people like, and I'm asking you guys to put in the portal because that I can keep track of it and give you points. I don't want to do all the record. Also, I want the self-reflection, blah, blah. But also you'll notice I put up a portal, like as per your suggestions, I did put up a portal that says anybody that's actually been super on time for the first 4 homeworks, so you won't know until we do the next one. But if every single of the 4 homeworks, your first attempt actually went in when the thing was due, even if you then revised it later, even if your first attempt was bad, but if you actually made an attempt to get the thing in, like when it was first due, then yes, I made a portal for that. So you could be rewarded for that. And it's like over 100 points. So that was a great suggestion. I also made another portal that subtly suggests that if you use the YouTubes at all and you use them in any kind of way that you can show, then you can get points for that as well. And that, I think the easiest way is like, yes, if you subscribe, you can get points. So I sort of took that suggestion, but it doesn't have to be subscribing. There's other ways you'll read it. Okay. One last thing. Oh, yes, go. Sorry.
What does WIU mean again?
Oh, yeah, it means I have really bad handwriting, because what I'm trying to say is WIQ, which is and very fair that you're asking, which is supposed to mean what is the question? Like please, like make the question super clear to me before you start answering it. Even if you just abbreviate, like you could just say like solve for X or something, but it means like on its own line, like make the question clear and then start answering. Does that if that makes sense? So it stands for what is the question? But my handwriting is bad, I guess. Wait, did that answer, Edie? Was that Edie? Sorry.
Yes, it was me.
Okay, and did I mean, does that make?
Yeah, that's fine. I just realized I had to just continue reading all the typos. But okay. I'll resubmit.
Okay, yeah, great. Okay, cool. And again, for everybody, it's not about shame. It's just about, I'm just trying to show you the way I can what I need ultimately. And it's never too late. To everybody too, I would encourage, like the more, again, you want to think of this as all practice for publications or for research or whatever. So every bit of math that you do, like every step, do try to put on its own line. Like that is sort of the tradition, and there's a reason for it. So like if you write on the first line, what solve for f, then on the next line write like f equals negative kx, and then on the next line plug in the numbers or whatever. Like unfortunately, the flip of what I'm saying is do please like use a lot of trees, like use a lot of paper, skip lines if it makes your work that much clearer or neater. Like you do want to spread out your thoughts in space and time. It makes them much better thoughts for you, and it does make it much easier for me. to manage. I should also quick note, whenever I say to anybody, what is the question? I will admit that part of what I mean in that also is like, what's the setup of the question? Like, it's true. Again, assume that I don't know. So you want to, so like in math methods, in homework 2, you would write something like x equals a cosine omega t, so dx dt equals question mark. Like, say the function is this, that's given. The question is, what's the derivative of the function? Like, you know, just enough so that someone can handle this and see if it's right or wrong without any outside sources. Like, that's basically the idea behind what is the question. And it, okay, all right, we're about to oh yeah, cool. No, and I appreciate there's a lot in the direct chat. I appreciate your appreciation in the direct chat. Thank you. Yeah, if you're struggling with calculus, I saw at least 2. All right, this is sort of what I was trying to say at the beginning. Well, I'll say more and more about this, but I saw at least 2 homeworks where I saw and I think they were homework 2, and we will get to that. I saw an honest struggle with calculus in at least 2 homeworks. When I say honest, what I mean is I saw someone writing things down that, okay, yes, they showed that they didn't totally remember. I mean, they were writing things down that were not totally right, or they weren't totally like following the rules, but they were writing a lot of stuff and really trying to work it. And they were trying to like make things work out as best they could. That's what I mean by an honest struggle. And I do give a lot of points for that. Like, by the time we get to the exam, yeah, we want it to be like even more correct than that. But the first rule of thumb is if you're struggling, especially with calculus, the more you can write, you will do a lot more for your struggle than you might think. And that's, I'm saying I commended at least 2 people on the homework for doing that. Like, they were getting things wrong, but they were willing to get things wrong. They were writing stuff down and showing what they thought. That's super helpful to them and to me. If I'm going to help people through calculus, the crucial thing is for me to know exactly where you are or where you've lost the thread. It's also crucial for you. So the first thing is, if you're struggling, writing down, and I mean more than, and I'm saying these 2 people that I really, and they didn't get full credit on the homework because they did leave some other things blank, but they'll go back and they'll fill in those blank things and then they will get full credit on the homework. But I'm saying that at least 2 people in this room did, when they got to a part that they thought was hard and was calculus, and I knew they were stressed. I mean, I'm sure they were stressed and annoyed that this calculus thing came up. They wrote stuff. They didn't just write, I have no idea. They didn't just write, I don't remember calculus. Like, that's good to write. That's helpful to me. But they also attempted, like they actually wrote math stuff. They were willing to put ink on paper even when the ink was going to be wrong. That is the most, possibly the most important skill that I could get across to everybody at any stage of hard science research, is you've got to be willing to be wrong on paper. Like, you've got to be willing to have other people see where your struggle is. So the first thing I'm saying to anybody who's admitting, including somebody in the private chat who's admitting, I'm struggling with calculus, what should I do? I'm saying you already did the first really important thing, is that you totally let me know and you admitted to yourself. That is cool. I'm not saying I'm going to get you to whoever you are in the private chat and in the homeworks. I won't be able to solve your entire calculus problem overnight. I won't. But I will be able to get you a lot farther in calculus than you might think. To all of you, there's a lot of calculus in this class. But for me, secretly, one of the big, it's not a secret, one of the big agendas of this class is for me to straighten out calculus, both for people who think they're never going to get it, and for people who that think they already got it, but in fact only know how to do it and don't actually know what it means or how to apply it or when to apply it or what its purpose for is in anything other than a straight up calculus exam. I'm actually here to teach you all calculus if you want to know the truth. You do have, even those of you who think you already know it. And I don't mean that in an obnoxious way. But in order for us to all do it together, we got to do a bunch of calculus to see it in action. So the first thing I would say is, yes, admitting to me that you don't like the calculus is good. Admitting it on homework is good. Following some of the tips and tricks that I put in the sheet that's called knowing what to do when you don't know what to do. Like, some of it's hard to follow, but some of it's not. Doing those tricks is good. But then also just like, and knowing that I was so bad at calculus, especially integrals. Integrals went over my head the first 3 classes I took in them. I mean, when I was an undergrad, I thought I would never understand integrals. And I took the courses, and sometimes I got good grades and sometimes I didn't. But like as long as you guys know that I know that we don't learn things necessarily just because we got through the class or necessarily the first time we see them. We learn them by going over and over and over and seeing them in action and stuff like that, and trusting that even if it's confusing right now, as long as we hang with it, it might get clearer tomorrow. So the one thing, to those of you who are very worried about this calculus, do keep taking notes. Like, I will keep giving you my PDFs, but don't just rely on those. Like, take your own notes while we're going through. While you're taking notes, make a mark of anything that you need to go back to later, like anything that's not clear right then. Even if it's not clear, don't stop taking the notes. Don't give up. Just note the difference between stuff you get and stuff you don't get. Hopefully everything you don't get, you'll get a chance to ask me at some point in the class or outside of class. But even if you don't get, well, hopefully at least outside the class, but just continuing to take notes and continuing to follow what we're doing, and just always marking what you don't understand and have to go back to versus what you do is a huge part of the process right there. And knowing that as long as you guys know that I know that I'm doing a lot of calculus here in order to get it across, not because I actually assume that it's actually comfortable to any of you. I don't actually. I know you've all seen it, so I can use it. But I'm actually here to try to go through it many times and try to unpack it for possibly the first time for many of you. That's actually my mission. So I trust you if you trust me, and bear with, like, to all of you. If you're fuzzy on the calculus, just keep taking those stuff, mark down what you don't get, and certainly stop me. Like, once I'm going, like, you can stop and say, wait, I don't get the chain rule or something. If I have to, I might say, I can't re-explain it right now, but duly noted, and I will re-explain it later or something. But if you don't want to do that publicly, do it, in the private chat. Even if I can't stop right then, it's important information for me to know. And I will not embarrass you. And I will not be like, well, there was a prerequisite for this class. No, the prerequisite thing is nonsense. Okay, physics should be a prerequisite for calculus, not the other way around. Don't worry about that. All right, I'm going to keep going on in a second. I hope that sort of helps for the moment. And again, you can always resubmit homework for that reason. Like, you might not remember the calculus now, but it might start to gel, or at least the calculus that we need might start to gel in a couple weeks, and then you can resubmit. But okay, I'm going to go back. Wait a minute. Oh, Catherine's comment is funny. Okay, and good afternoon, Shamar. Okay, wait, I'm still catching the chat. Oh, that was you. Okay. That was me. Oh, that was me. Okay, cool. All right.
Professor?
Oh, yes. Sorry, Caleb. Yes, go.
How do you do a game you subscribe?
Oh no. Oh, that one. Wait, you didn't get it, or you didn't do it?
I didn't understand what you have to do for that one.
Okay. So that one, thank you for asking. That's a totally fair question. So that game, that's one of the many like special game assignments that you could do at any time. I mean, really, all of them you could do at any time. But that one is not a nightly thing. Basically, what that's saying is, if at any point in this course, you either like actually you could screenshot. If at any point in this course you actually use one of the YouTube videos in any way, like, it doesn't mean even watching it all from beginning to end, but like if you used it as a reference, or you had it on the background for like 15 minutes or something while you were cooking dinner, or you subscribe, or it's like anything, if you use any of the YouTubes in any way, and you could sort of tell me that. I mean, you might be able to prove it with a screenshot, but even if you can't prove it, it's not about proof. If you just write me a note that says like, I actually listened to 2 hours of the second video while I was cooking dinner, and it helped. Like, now I understand springs better, or something. Just if you use the YouTubes in any way as a resource, you could submit that for points, like one time. And certainly subscribing would be one way to do that. And this is partly because someone suggested the other day, could we get extra points if we subscribe? And I have mixed feelings. I kind of want to give people extra points for subscribing, but I kind of feel like that's ethically shady. I'm not really sure if I feel, so I'm just generalizing it and saying, if you can like show or convince me or just tell me that you've used the YouTube in any kind of useful way, including subscribing, then you get points for that. Does that make sense?
Yeah, I get what you mean. All right.
Cool. Okay. So that's that. And that's also, I also put up another one, I think. Oh yeah. So that's the other one. So I'm just going to keep putting up things like that. Again, the rule of thumb here is that anything anybody does that's like extra good or right, I want to acknowledge, reward, and be happy about. But anytime anybody does anything extra wrong, or anytime anybody doesn't do something right, I don't want to punish that. It's just about like, it's good versus better. There's no bad, like that's my attitude to all of you. So I'm just trying to come up with systems where anytime, and I want you to know what I think is really right in physics. So I'm just trying to give points for anything that I think is a smart, cool way to go through this class and do physics. Speaking of which, quickly before I forget speaking of which, and we're going to get back to the homework, and I always feel bad about how long I take talking about these things. Hold on. But you know, again, I love physics, and I've been doing it for a long time. Like I went to college, I was a physics major. I was also a philosophy major, actually. But then I went to graduate school twice. Like I've been studying it for a long time. But that's part of the reason that I can come across now, like secure about the parts of physics that I know. The parts that I know now, I know deeply because I've thought about them so many times, but I had to think about them so many times to feel that comfortable with them. I've gotten some very bad grades in my time in physics, believe. I mean, really bad, like it, and I found school very stressful. I still do. So I'm just trying to maximize the intensity to stress ratio for everybody. Like the more intense we can be with the less stressed we can be, I think the better for everybody. So on that note, very quickly, I want to just quickly say this. So this, I'm going to say this quickly. It might bother some people. Just to be as clear as possible. Yes, I've turned back about 6 or so of the homework 2s, and those people can still get more points if they want, but I just want to acknowledge right now, just to be as clear as I can, this is not to embarrass me, that the following people totally turned it in. The following names, you totally turned in homework 2. I totally know that. And I just haven't gotten to yours yet, just for like alphabetical or other random reasons. It's nothing personal. Like your homeworks look great. I just haven't gotten them back yet for like no good reason whatsoever. And that is Matthew, Alvarez, Jacob, Noelia, Shomari, Jean, Liani, Molly, Jitlalia, Shankia, and Yasmin. I totally know that you totally turned in these homeworks totally very much on time, and I appreciate it. And I haven't gotten them back to you yet for no good reason, but they're coming back soon. So, okay. Other than that, I think anything that everybody's done has come back so far, and we're going to keep trucking. Now, I think if there's no other questions, I think, but you still can't ask for questions. Okay. We're going to go back to the material. Yes, that's it. Hopefully you can see the screen. Okay, I'm readjusting things. We're going to get a solution. We're finally going to get a solution to this question 9 of homework 1. Okay. Right. Okay. So, and again, you could stop me anytime. I'm just shifting gears here to actual physics, but definitely stop me with whatever. As we're going. All right. Okay, let me make this very clear, as clear as I can. I always, the most important thing always gets crammed at the bottom of these pages. But all right, we have a differential equation here that physics has brought to us. It's a second order differential equation. It is second derivative of x with respect to t equals negative k over m times x. Oh, I should say also, yeah, that's what we have. We have that equation, and it's an equation that has a bunch of letters in it. Remember, these letters K and M are constants, right? They might as well just be numbers. In fact, in the actual problem that we're looking at that we started this semester with, they actually like are numbers. K is 200 and M is 0.3. And those numbers never change throughout the problem. To call them K and M is to acknowledge that we don't really care whether it happens to be 200 or 300 or whatever. It's just some number that depends on what laboratory we're sitting in, what particular pieces of equipment we happen to be playing with. But whatever number it is does not change throughout the situation. Whatever number it is does not change while the mass goes back and forth along the table, and does not change while the clock ticks, right? So K and M are constants. X and T are the variables. One of the variables depends on the other. And you can tell that by the way they're written. Whichever variables in the denominator of a derivative is always the independent variable, and the other one is the dependent variable. So we have this equation that tells us something about the derivative and how it relates to the dependent variable. It's saying the rate of change of the rate of change depends on the thing that depends. That quirkiness that I just said, the fact that the rate of change is a function of the dependent variable, the fact that the rate of change depends on the dependent variable is bizarre. I'm going to keep saying it like throughout the whole semester. If ever you hear me saying, you're like, wait, what did he just say? He just said it depends on the depends. Then you get the whole issue. If I didn't say that, we wouldn't have a differential equation. What makes this interesting is that the rate of change depends on the dependent variable. It is circular. In this case, again, what we're saying is acceleration at any moment depends on position, whereas position is something that we don't control in the lab. Position depends on time. So we have like this dependence chain that is funky. We're trying to unpack it. We're trying to solve this differential equation. To solve it means rearrange things, unpack things so that we have a nice, clean, simple rule that says how the dependent variable does depend on the independent variable, like the way life should be. We want x as a function of t. We want a rule where you plug in t and what comes out is x. That's so once we get a function x of t, that is what we mean by a solution to the differential equation. Let me put this one last way. Often people at this stage of science or math they get used to thinking that we use formulas or equations in order to solve problems. They think they get questions and they're looking for answers, so they use formulas to get the answers. I'm saying no, when you're really doing physics, when it's at least really physics, especially if you're really doing it, if you're doing research physics, often equations are not what you use to get the answer. Equations are the answer you're looking for. We're looking to determine a relationship between where this thing is and what time the clock on the wall says. So when we get a function x of t, that will actually be our answer, our solution to this thing that looks like just another equation, but is actually a puzzle to be solved. It's not a final landing place. It's a puzzle to be solved. We're looking for an x as a function of t. How will we know when we've gotten there? How do we know we have a right answer? What is a right answer? Well, we're looking for, now I'm reading the English on the page, like to solve this differential equation means we're looking for an x dependent on t such that when you take the derivative of x and then you take the derivative of that, when you take two derivatives of x, because that's what the equation says, we're looking for an x such that when you differentiate it twice, you get back x itself. That's what this equation says, that we want some kind of function where if you differentiate it twice, you get back itself, but times some constant or bunch of constants, and then times a negative sign. That's what's written here in the red on the bottom of the page. It's got squeezed, but it's like kind of the most important thing on the page. We're looking for an x, some kind of x, such that when you differentiate, when you take two derivatives of it, and again, we'll go through derivatives again. Some of you are more comfortable with them than others. And some of you, as soon as you see what I'm doing, you'll be like, oh yeah, I remember that now. We're looking for an x function such that when you take a derivative and then take a derivative again, because this thing said second derivative, that you get back that x function, but times like k over m, which are just constants, right? And then times a negative sign, times -1. And that's how we'll know we've done it right. Once we have a function, once we have a function that we think is right, and that's what we're about to do, we're conjecturing and verifying, we're going to build a function that we think is right, a rule, a mapping, whatever, a relationship. And then if we think it's right, we're going to take derivatives of it. We're going to differentiate it with respect to time twice and see if what pops out is that original function times some constants times -k. Remember one last thing. Sorry. Okay, just remember when we were doing sidebar 1 and sidebar 2 yesterday, and I know for some of you, it's like, what does this all have to do with anything? I was trying to show you some math ideas that are important here. One is that constant just means a letter that stands for some number that we don't know what it is, and it doesn't even matter what it is, but as long as it doesn't change, right? So, what does it? Oh, great question, Shankia. All right, well, the quick answer is it means equal by definition. But so that's the answer, but that's a great question. I'm sorry if I haven't made that clear yet. I want to dwell on that in a minute more. But yeah, great question. Hold on. Yeah, well, okay, for everybody. If I ever use 3 and yeah, good. Right. I even want to, all right, I'm going to write that right now, but that's good, Jacob. I mean, good question, Shakia, and good answer, Jacob. And you should both put those in the game thing. But okay, actually, let me sorry about that for a second. Yeah, triple equal signs are stronger. This is Jacob's point and response to Shankia's observation. I live for triple equal signs. Triple equal signs are stronger than double equal signs. Triple equal sign. There's two types of equality in physics, I think, in life. There's two types of equality. Well, maybe there's three, but there's basically two in science. Equal by condition, observation, or circumstance. That's a double equal sign. Or discovery. That's a double equal sign. When things turn out to be equal, and that generally means that they're generally equal, or they're equal in the context that we're talking about, or we've discovered that they're mostly usually turn out to be equal that way. That's double equal sign. Triple equal sign means equal by definition, and means they have to be equal. It would be a contradiction if they weren't equal. You can't find a circumstance where they're not equal. And anything that can come back to a triple equal sign, or anything that we can, and often then when you're, and this is kind of like the third meaning, often when you just define something for the first time that way, if you say, let C3 be the name of C1 minus C2, like, then you use a triple equal sign there. So it doesn't necessarily mean it's super important. Triple equal sign doesn't necessarily mean that everybody's always cared about it since the beginning of time, but it means it's established by language. So if you say, let C3 triple equal sign C1 minus C2, you're saying, I'm just going to use the symbol C3 from here on in to mean the difference between C1 and C2. So anytime you see C1 and C2, you can sub in, I mean, C1 minus C2, you can sub in C3 from now on, because I just made it a rule of language. So it's not a discovery. It's not claiming anything about the numbers C1 and C2. It's saying, this is the way we're going to use the language from now on. And people in this class who maybe do computer programming and stuff are familiar in a different way with this kind of concept. But it's a really strong, important concept. And I'm glad Jacob added to it, like, because once you have a triple equal sign, you can rely on it. It's not discovered in the laboratory. It's true. Otherwise, there's a contradiction. Okay, so good question. I mean, I hope I answered that. So what I'm saying here to everybody then is like just like we were playing with constants yesterday in the derivatives we were doing, and we were just saying things like, oh, if C1 is a constant, is some, oh, thank you. Awesome. That's so nice. See, I'm going to put a portal for that. All right, I'm totally going to put, if I don't forget, remind me, I'm going to put a game portal in for any time anybody like closes the loop on a conversation. I'll think of a word for it, or like acknowledges, like what Shakia just did. And it's not just because it's polite, but it is super polite and it does make me feel good, but also just, it's good communication. It's like putting a tap back in text messages or whatever, which I love. I mean, it's just a way of saying, oh, okay, yeah, like communication achieved. We can all move on now. Like totally helpful. I'm going to put a portal for that. If I remember. Okay, especially with a person like me, it's important, because otherwise, as you see, I'm never going to come back if you don't bring me back. So yesterday, yesterday I was trying to say, like, if you have two constants, but you don't know what either of them are, then you can combine them into one, and what you have is one constant still. If a constant means a number that won't change, but that we don't necessarily know what it is, we can play with constants in a way that really cleans up and simplifies our life. We can think that we have a whole bunch of unknowns, but if we combine them all together, they're just one unknown. So similar here, I want to point out before we go any further, if K is a constant and M is a constant, then K divided by M is just some constant. I could call it something else. We could say, in other words, and I'm not going to just yet, but I will, different color. We could say, we can make up some name. We could say for now, instead of K over M all the time, we could call it C4. And it would be just that constant that represents the spring stiffness divided by the mass. And I'll even go one step further. Since we can call it whatever we want, we could even call it C4 squared or C4 cubed. And it still would be a constant. It'd be a funny name, but it would just be a name. And in fact, we are going to do something like that. So I'm warning you, like, just note that if K and M are two different constants, then we can combine them together, make it a constant, and call that constant whatever we want, okay? But what we are looking for, to go back to this, we're looking for some function of t that we're calling x, such that has constants in it, but it has t in it as well, and such that when we differentiate it twice, we get back itself times some kind of constant, but then times the important constant -1. Like we want to get something that flips its sign when it comes back. And why am I saying all that? Because that's what this says here. It says x, it says that the second derivative of x is equal to negative times some constants times x itself. So that's the kind of x that we're looking for. When we get an x that does that, we have solved this differential equation. So what I suggested, like twice now, I mean, I suggested yesterday and I suggested last week, and I think that some of your early lab, oh yeah, okay. Right. Okay. Awesome. Okay. So I was about to write it down, but then Avery Yeller. So this totally, he should put in the portal for points for right or wrong. Yeah. So Avery Yeller is, and again, tell me if I'm saying the name wrong or if I'm not saying the first, but anyway, I think that, but he says he's guessing that the type of function we want to solve this differential equation is going to be either a trig function or an exponential with a negative argument. So clever and so right. And again,
I think that's wrong. Actually, I typed too quickly. But if it were to be a negative argument, then it would be positive on the second derivative. I was just thinking too quickly.
Okay, all right. Well, all right. First of all, you still totally get points for that, karmically and academically. But good, correct. All right, you get point. Oh, I'm gonna put that. All right, that's gonna be a portal also. Seriously, if I don't forget, I think there's also gonna be a portal for a self-correction. Because that's good. That's totally. I mean, I like what he originally said. I was going to start talking about the negative sign, but he caught. I mean, Avery Yeller caught it faster than I could. So yeah, I gotta remember to put a portal for that. But all right, here's the deal. He's still right. Like I still think he's like largely right. He's guessing types of functions, partly either based on his personal experience or perhaps based on what we've been saying for the last 2 days, or for some of you, it might be consistent with what we're saying the last 2 days. What I was trying to show yesterday to everybody is that certain types of functions are not going to work here. Like x equals 1/2 at squared is an example of x as a function of t. But it's not a good function for this purpose, because when you take two derivatives of x equals 1/2 at squared, you just get a. Like you just get a constant number. You don't get something that still has the x in it. What Avery Yeller's saying is, oh yeah, if you want something that even upon differentiation, even upon taking derivatives, spits back the original function, you need a funky kind of function, like the exponentials we were playing with yesterday, or trig functions, because at least for anybody who remembers, when you take the derivative of sine, you get cosine, but then when you take the derivative of cosine, you get back negative sine. So it totally does seem like with trig functions, when you take two derivatives, you do get back to the original, but with a negative sign. But then what Avery Yeller said, so totally, and that's what we're going to use. He also threw an I still want to praise. I know he just took, like, for the record, I understand he totally took back the second thing he said, and he's getting points for that. But I still want to resurrect it for a minute anyway. Like, it wasn't crazy for Avery Yeller then to throw in exponentials into the discussion as well, because we spent all that time on it yesterday. There must have been a reason. Exponentials are cool generally in that when you differentiate them, you get them back. And that's what we're looking for. However, what we are looking for here, and again, he said this, like I'm not correcting, he said this already, but what we're looking for here is something that when we get it back, we get back with a negative sign. And part of homework 2 that 10 of you have totally done and I haven't given back in, and I'm sorry, and 6 of you totally have done and you haven't gotten back, but you're going to get more points soon. But if you've looked at homework 2 at all, you'll notice at the beginning, or on the second page, I'm playing with these examples with you for this reason. I'm trying to get you to see that, oh, exponential functions, funky things happen with the negative sign, like not the way I want, even when I stick the negative sign in the argument, as Avery Yeller suggested, which seems like a smart thing to do. The chain rule kind of pops it out too cleanly, and the negative sign doesn't do what I want it to do. Like exponentials get weird with the negative signs. That's what homework 2 is sort of trying to show at the beginning. So yeah. So to bring it full circle, both because Avery Yeller said it, also because I said it yesterday, and also because your lab data strongly suggests, I'm going to go back to what we conjectured. I'm going to say, and we're finally going to get somewhere with this. I'm going to conjecture cosine. Now, I'm leaving blanks for exactly the reason I said yesterday. Like I'm conjecturing that the type of function I want is cosine. That's the type of function, but there's still going to be I'm leaving room for tweaking details because there are going to be details. As we said yesterday. Oops, sorry. As we said yesterday. So number one, oh, sorry.
Yeah, so based on you're doing this based on like the second derivative we saw before, right? That it kind of resembled.
Right.
Okay. But that's not enough to prove that it's cosine, but you can check
Right.
that.
Exactly. That's why I'm thinking of it, but it doesn't prove it. But that's where the motivation comes from. Yes, exactly right. And yes, that's awesome. That's also points right there. Oh, sorry. Go.
What's it called?
What does it say after guess?
Oh, sorry. Oh, it says, wait, it says guess. It says guess. Oh, yikes. It's trying to say guess a cosinusoidal type of function, but leave space. Sorry, but leave, oh my God, but leave space for arbitrary constants with units. Sorry, wait, should I say that again? Was that cool, Juanita?
Yes, Professor. Thank you.
Okay, thank you. Okay, and back to you.
Yeah, a related question. df, like this, so some function in f, right? The second derivative of f with respect to t times dt. Real quick, can you tell me what that means?
Oh, you mean, wait, if you have the second derivative, but you try to multiply it by just one differential, like you're saying
dt, yeah.
Yeah, you can't really do that. It doesn't really mean, that's a great question. I think I understand where the question lives, but it's kind of an error to do that. Now, it's quick sidebar why.
Okay.
I
couldn't understand if it was like multiplying it by one or if it gets rid of the dt.
Right. Okay, and that's totally why. It's a great question. I'm going to try to say something quick to everybody about that. It's a great question. Sorry, hold on. It's a great question because sure, based on everything I did yesterday, that would be what I'd want to do. Like the easiest thing to do here to unpack this would be to follow the model from yesterday. But so yeah, that's a good thing to look into, but it doesn't really work. It doesn't really mean anything for this reason. Actually, I'll say to everybody, and this might clear up something to everybody again. So he's asking, I think, a sophisticated question, but I want to say to everybody that my answer, it might look sophisticated for a second, but actually it might help all of us who are still trying to remind ourselves of fundamentals. You'll note that this thing here, d2x dt squared, like that means second derivative of x with respect to t. I mean, I think you've all seen that before, but you know, many of you might be like me. When I saw that the first 100 times, it bothered the tar out of me. It really bothered me because the 2 is right after the d, but then in the numerator, but then the other 2 is after the t, right? It looks totally random how they put the 2's in there. And by looking, and at first I was like, that doesn't make, wait, is that a typo? Like, what is that? And then when I learned, or someone told me it wasn't a typo, that's the way it is. What it did to me, and it might do to some of you without realizing it, it just was another piece of evidence that like math doesn't make any sense. And it's just a bunch of random decisions that people in power make. And like, they just like scramble up these things and put the 2 wherever the heck they want. And so it reinforced in me a lack of desire to take this notation seriously. It was like, all right, that's just another thing to memorize. I'll just accept it because this crap does not make sense. And they clearly don't even care if it makes sense. So I'm just going to memorize that means second derivative. And I can't really do much with it. I'm just going to like accept that it's a second derivative. That's what happened in my brain. And I'm not even saying I knew that my brain was doing that. I'm just saying that that piece of notation was one more step in a long journey of being turned off for a while to all this math and turned off to the idea that it actually can be figured out by us. Let me show you, and if you didn't have that reaction, good, but let me show you all that this actually does make sense. What's really going on here, what this really means and how to use it is this. It equals, it's by definition means derivatives. So please write this down, like everybody. I mean, this is in response partly to what Caleb just asked, but it's a good thing to think about when you're trying, to understand derivatives. What I'm saying is that a derivative is a ratio of differentials. I mean, it is a fraction, but first and foremost, even before you think of that, a derivative is an operation. Let's back up and say this. A function is a box, right? A black box. You put a number in, I pop a number out. Like that's what a function is. It's a rule. It's a mapping that tells you for any given input of some number, we've got a rule that tells you what number pops out, right? Like y equals mx plus b, you pop, tells you what to do to x so that we could pop out a y. Okay, functions are number goes in, number comes out. Operations are things that we do to functions. Operations are black boxes where you put a function in and a function comes out. So why am I saying that? I'm saying when you differentiate, it's not something that you do to a number. A derivative is not differentiating is not a black box for numbers. It's something that you do to functions. You put a function in, I take the derivative, and what comes out is a function. Okay, so operations are to functions as functions are to numbers. And when you write dx dt, like the first derivative, when you write this thing, dx dt, like velocity, like the first derivative of position with respect to time, one way to think about it is you take the x function and you look at the x function and you're taking the time derivative of it. You're taking derivative with respect to time of x. Like that's what dx dt means. It means something that you're doing to the x function. You're looking at the rate of change with respect to time of the x function. So then when you take another time derivative of it, you now have the second derivative. The second derivative is what happens when you take the derivative of x. So the reason the twos are written in that funky way is it actually does make sense. The reason that it's written d2 squared is because you have ddt of x. That's a sidebar. Again, it doesn't mean anybody's question was wrong at all. But it's also partially to illustrate an answer to Caleb's question why we then once you have dt squared in the denominator there, it doesn't really mean dt times dt. It really means dt of dt. And that's why you can't actually just multiply out one by itself to the other side the way I wish we could based on yesterday's lecture. Like that's why it was a very good question. But the d2 really means time derivative of time derivative. So that's why in this second derivative case that physics has brought us, here, so we have a second order differential equation. Everything I did yesterday, and again, this could confuse people, everything I did yesterday was trying to kind of show what a differential equation is. And I was doing it through the example of a first order, which is hard enough. But now physics is demanding that we go to the second order just like right away, because that's just space and time. It's just presenting that evidence to us. So we have a second derivative. I'm not going to be able to use the method of yesterday. I'm using a method of conjecture and check. So I'm conjecturing, or another guess and check. So I'm guessing a cosine function for precisely the reason that Avery Yeller said, and Caleb said, and other people have said. I'm guessing a cosine function. One last thing you might be thinking, and you might just be thinking that you shouldn't be. You might be thinking, okay, I kind of get this, but he keeps saying trig functions. And he keeps using examples like, okay, derivative of sine is cosine, derivative of cosine, negative sine. So somewhere in your mind, you might be thinking, why the heck am I not using a sine? Or you might have seen on the web that they use sine And you might have even put in your homework sine. Why am I not talking about sine? If that's bothering you, that's a very legitimate concern. Like, you're not dumb if you think you're confused because you're wondering, where did I get and it's not because I'm a genius. I mean, I'm not a genius, but it's not because like 3 people in the room are geniuses that they picked up on cosine. I could use sine is the fact. I could try sine, but it's going to take a little more work to make sine. So here's the next sidebar. Hold on. Or also, depending on where you looked on the web, you might notice that some people start when they're dealing with this stuff. They start with a combination of both. They're just as confused as you. It's not confusion. They're just more cocky about it. They're like, well, it could be sine or cosine. So I'm going to start with a function sine of t plus cosine of t. People do that, and then they play with it to see what cancels out or what works or whatnot. And so none of that. So when you have those thoughts, don't think this means I don't get it. It probably does mean that you probably do get something, which is why it's always worth writing down whatever's confusing. But here's my answer to why we're starting with cosine rather than sine. It's simply this. It's simply that the sine of 0 is 0 and the cosine of 0 is 1. That's the reason. It's that simple. Like, this is sine, right? And I never hope I'm not going to do this one. I did well, didn't do it very well, but this the brown thing cosine starts with a y-intercept. Sine does not. That doesn't mean sine is a bad function. Sine's a beautiful function. That way it's like nice and simple. Sine, but that's not what we probably want here for this physical system, because our physical system, when time was 0, the position was not 0. The mass did not start at the equilibrium position. If it had been at the equilibrium position, it would never go anywhere. It's right. So we want a function that actually starts somewhere off the origin. That's the reason I'm starting with cosine. It just seems more directly descriptive of the physical situation that we're talking about. And this is a physics class. All right, so that's a sidebar too, but there's ways if you did math, if you did homework too, you'll see we eventually started playing with functions in a way that could make sine work. Like, we could make it work. It would just take more work. So I'm starting with cosine and getting back. So again, I have, and I can turn back at any time if you want. So I have. All right, let's
Are you going to try to prove this now, Professor?
Well, I'm gonna fill it out and try to prove it. Yeah, I mean, I'm gonna.
Gotcha.
Well, yeah. So I'm gonna. So in order, I need something to prove. I need to prove that an actual function that I've written out is actually correct. So here, I'm gonna write out the function. First, I'm gonna say. Okay, this is where I'm going to start converging on things that people might have seen on the web. I'm going to give a name. I'm saying, all right, to everybody, I'm saying one of those blank spaces, there has to be a letter there. There has to be, I mean, there can't be any more variables. We're just looking for one variable function of one variable, but there's got to be some kind of number or a letter there that's measured in radians per second, because I need set radians per second on purpose so that the seconds cancel out with the seconds of time. And I'm not being asked to take the cosine of, I can't take the cosine of a second. I can only take the cosine of a radian. Or technically a degree, but we don't use degrees really in higher math or physics. They're like very inconvenient. But you can only take the cosine of an angle, and angles are measured in radians. So I'm going to have to put some kind of letter or symbol there that is measured in radians per second. So the seconds cancel out and I'm left with radians. I could put any symbol there I want. I could put K there, but I have no reason to assume, but K is not measured in radians per second. It's measured in newtons per meter. I could put M there, but that's measured in kilograms. Maybe what I'm going to end up finding there is some combination of K and M, but I don't know that yet. I haven't proven anything like that yet. I just know something's going to be there, so I'm going to give it a name. I could call it C3. I could call it C1. I could call it C. Actually, what I'm going to do, though, is since I can call whatever I want, I'm going to call it lowercase omega. This is the thing that a lot of people found on the web, like on the first day, and I don't know if they knew what they were finding or not, but this letter here in blue, this Greek lowercase letter is an omega. I could use whatever I want, but I'm using this because it's what everybody else uses. And with the benefit of hindsight, it turns out to be a convenient, it turns out to match up with some other things that are nice, lowercase omega. And I don't know anything about it yet. Like Caleb, I think it was Caleb just asked, like, I'm going to have to prove something in a minute. I definitely haven't proven anything about omega, but there's nothing that I'm even saying about omega yet, other than it's the name for something measured in radians per second. In other words, in this class, okay, I always use brackets, like square brackets, to refer to units, meaning if I write something like this, if I write something like that, like bracket omega equals bracket radians per second, I'm just saying that the units of omega must be radians per second. Like by definition, I know that omega because that's why I'm putting omega in there. And that's all I know about omega. I'll warn everybody again, anybody who's still paying attention. I know it's super annoying and out of left field that omega is a Greek letter and it's lowercase. And it seems like I'm all of a sudden introducing something like, wait, we don't know anything about omega. Like, why is omega coming into this? Wait, did he teach us about omega? I am teaching you about omega right now for the first time. There is nothing to be known about omega, no background knowledge or material. It's just a letter that's standing for something that's got to be measured in radians per second. Otherwise, this function cannot be proven correct. Like it's got to be in radians per second. And meaning,
I don't know if it'll help, Professor, but in lab we got to sort of the fundamentals of simple harmonic motion. If it helps for you to know that we know that for this.
all right, cool. Actually, that does help me to know that. Thank you. That I keep meaning to ask that. Thank you. That totally does help me. So
Yeah.
okay, good. So I can speed this along a little bit more. Okay, and as long as you're saying that, thank you. I've been keeping, and I keep texting with Wu. But so you did lab 1, which was spring, and then you did the pendulum lab, and you talked about simple harmonic motion. You're saying.
Yeah, he gave us 3 rules that only apply to simple harmonic motion, and that double the second order derivative to the negative whatever. He showed us how all of those equals sort of a Hooke's law form, and all of those that can be applied to so far.
Oh, great. All right. No, that does save me. All right. That good. Thank you. So I will do this a little bit more. Okay. That's great to know. It also means he's not fired. No, I'm just kidding. No, that's great. Thank you. All right. So then looking in the chat. Okay. Yeah. All right. So right. So then good. So I don't have to speak so abstractly. Like, so you all know in a way, and you know from math anyway, that if you have a cosine function going back and forth, representing, for example, your mass on your spring in the lab or your pendulum, the higher omega is, the higher that number, that argument in the cosine function, the higher it is, the more quickly this the cosine function cycles or wiggles, the more bumps it makes per unit on the horizontal axis. The more bumps there are per unit time, because the horizontal axis is measured in, sorry. The horizontal axis is measured in radians. Put one last final way to people who are getting, like, meters per second is a rate of speed or velocity, right? Like meters per second is how much space we cover per time. This is not that. This is radians per second. It's still some kind of a rate, but it isn't a rate of space per time. It's a rate of cycles per time, or sections of a cycle of a circle, which we call radians per time. So omega is the rate at which this thing wiggles back and forth. And that's all I know about it so far. And yeah, so I'm about to do the thing that Professor Wu did, just one more step. So far we have so far this is my function. X equals something times cosine of omega t, where omega is just this constant that refers to the rate at which how quickly the cosine function wiggles or cycles back and forth, and it's measured in radians per second. I want to fill in the other blank, and this is easier in a way. The other blank also is determined by units. Like when you take the cosine of 0, you get the number 1. You don't get 1 radian or 1 kilogram or 1 meter or anything like that. You just, the cosine of an angle is a number. Cosine of pi over 6 is radical 3 over 2, not radical 3 over 2 meters, just radical 3 over 2. So we need something here that's measured in meters so that this entire thing spits out an actual position measured in proper units. But here, so we're going to make up some letter for that. We can make up anything. We could call this another Greek letter, or we could call this C3 or whatever. But for this constant that we're putting in, we actually do know a little bit more about it already. Like we actually do have some perspective on it, because we know that when we plug in 0 into the cosine, into the argument, into t, and take the cosine of it, what we get is the number 1. We know, in other words, well, what I'm trying to say is this. We know that whatever position the mass is at t equals 0, wherever the mass is in the initial moment of this oscillation, again, at wherever the mass is at t equals 0, is what we call the mass's initial position. It's what we call x sub 0. Like again, I kept sort of doing that in yesterday's sidebars, saying x of 0 is the same thing by definition of what we call in physics x sub 0, x naught, right? So that's what we want this entire right side of the equation to spit out whenever t is equal to 0. But what it will spit out as it is right now, if I don't put anything in that blank space, what it's going to spit out is the number 1. Well, so just multiply the number 1 by x sub 0 and we'll have the correct answer. In other words, I'm saying this must go right here. X naught is like a scaling factor almost. Like cosine itself by itself is only going to range between 1 and -1 as pure numbers. But multiply that entire thing by 0.15 meters, for example, and then this position function will range, but not between 1 and -1 unitless, but it'll range between 0.15 and -0.15 meters, as long as we scale the whole thing by 0.15. So what I'm saying now, finally, not to keep Caleb in like itching for too long, or anybody else, because I see now, yeah, this is probably redundant with what we did, but hopefully clarifying for some people. We now have something to prove or something to test. I've now built my function. I'm about to write it down again. It doesn't mean I'm right yet. Like, this is why Caleb asked that. Like, I have to now prove something is right, but I finally have something to attempt to prove, something to test. And that's this, what okay, this is my conjecture. Now, again, this is like, I mean, this is really physics because I'm treating math like it's an experiment now, right? Like, I have a hypothesis and I'm about to test my hypothesis. And then if it's right, then I'm going to call it truth, right? And honestly, this is actually how math and physics work at the higher level. We don't know what we know before we know it. We try things out and then we find out if we're right, because the rules of math and science are that tight that we can do that. So I'm now going to test. This is a conjecture, like a hypothesis. We're going to test it or prove it to see if it's right. We're going to verify it. So we finally have something to test here. Remember, we have an, and notice, I don't know if it looks simple or boring or old, and yes, it probably does look old. If you've been paying attention in lab, it sounds like this should look a little bit old to you now, but okay. But what it is a function, right? It has x by itself on the left side. It is t on the right side. Everything else is a constant, including x naught. I should take pains to point out, x naught is not a variable. It's a constant, right? Because it's just some number. In the case of homework 1, it's the number 0.15 meters, right? That's all these things are. To be clear, this is a constant. This is a constant. Notice there's 2 constants in our expression. That's not a coincidence, and that's actually good sign, because remember, every time we have a derivative, in order to work backwards, we take a integral. And we saw 2 days ago that every time we take a integral, it pops out a arbitrary constant, like, because it's an indefinite integral, because we don't like know if we're doing this in general, where we're integrating from or to. So for every integral that has to happen, an arbitrary constant pops out. This is a second order differential equation. There's two derivatives that are being taken here. So it's not a surprise at all in a way that when we try to unpack it backwards, we would encounter or anticipate one arbitrary constant for each of those integrals, right? So this is a good looking function. It is x as a function of t, but has two constants in it placed in appropriate places. So like it looks good. It's built to test now. It has the form of something that might or might not work. What do I mean by testing it? I'm going to test it by differentiating it twice and seeing what happens. I want to bring us back again full circle to the beginning. And again, this is like anything else in physics or math. Of course, once you get it, then you feel like, oh, I get it. Like all the rest is just like boring detail. But until you get it, it needs to be said 52 different ways in order to get it. So like, you know, we're all talking to different people here at the same time. But again, also, hopefully for those of you who do think you get it, I hope you'll find that if you do get it, that means you can look at it comfortably without stress. And so please do. Like those of you who think who do know what's going on, soak it in. Because hopefully every time we look at this, something new is going to fall into perspective and into place and connect with maybe some of your other courses that you're taking or whatnot. Like there is a reason that I never find this boring. I'm saying that like, to all of you. Every time I look at this crap, something new falls into place. Because it is that dense and rich. Anyway, I'm saying, remember what we're trying to do. What we're trying to do is find some x such that when we differentiate it twice, we get a negative times a constant times x. So we now finally have an x function. We finally do. So I'm going to differentiate it twice and see what happens. That's what I'm going to do. And that's why, and this is also why those of you who are doing the math homework, those of you doing the homework, like some of you started the math, what I keep calling homework 2, you started like 3 days ago, and the first couple of questions may have seemed completely random to you. You might have known how to do them. You might not. But they might have been like, what the heck is this? Why am I taking derivatives of cosines out of nowhere? Now you see why, like, because we're just playing from this same thing from just a different direction. And those of you who were not comfortable with it, if you start it now, hopefully this will all start coming together soon. But I'm saying, okay, let's test. And yes, it's meant to fit with the lab too. I'm so glad that someone just reminded me where you are in the lab. Oh, was that a question or was that a squeak? Oh, that's a mouse. Okay. Everything does seem like a bunch of pieces at first, but really, we really do struggle to have all these pieces come together. Lab is not supposed to just be a random, like it really does have everything to do with what we're doing here. Sometimes it'll be ahead of us. Often it'll be ahead of us, but it is all supposed to fit together. But okay. And they're all written. They're not out of books, as you can tell, but anyway, whatever. Let's test. So the function that we're testing, again, is this. All right, so we're going to differentiate first. We're going to differentiate once. Now, does anybody oh, there's something in the chat. I was just going to, maybe that's, and if anybody wants to put the answer in the, oh, great question. Okay. There's a great question in the chat, in the direct chat. Will we ever use sine or do we always use cosine? The great question. In this class, we're always going to use cosine because it's a great question, but because the more you get used to this, the more you find that you always could use, there's always an adjustment you can make on cosine to make sine work and vice versa. In fact, you see that if you get to this point in the math, in homework 2, it gets to a point where it starts asking about like omega t plus 3.5. I don't remember if that's familiar, but you'll all see it eventually. And you'll start to see that if you're willing to add an extra term in the parentheses, you can always change a sine to a cosine or a cosine to a sine. Because of that, because you can get away with always using one, and because we're a physics class, not a math class, we always are interested in systems that start away from equilibrium, because if they start at equilibrium, they won't ever go anywhere. So in this class, we will actually can I say this with total confidence? Yeah, in this class, we will always use a cosine. That does not mean that sines aren't right. It just means that cosines always are, and we can get away with it. So good question. Yeah, I mean, we're always going to use cosine as the function. Yeah. I mean, we still have to like know how sine works and everything, but yes, we're always going to use cosines here. That is a good question.
But
Oh,
by
sorry.
equilibrium, you say that we want to use cosine because it starts out at 1, not 0, right? And 0 is the middle point in the interval that it can output.
Right. Exactly.
Got it. Okay.
Cool. All right. So I'm going to take the derivative of this. Now I'm going to pause for a second because if anybody wants to, for their own personal practice or whatever, if they want to shout it out or put it into chat or privately or publicly. And again, this is a moment where it's not a race. Like I'm just going to pause for a second. If like 3 of you put it in the chat, I don't care that one of you put it first and the other, like so I'm going to pause for a second. If anybody wants to put in the chat or shout out or anything, what the function is this. So the independent variable is t, the dependent variable is x. Remember, x naught and omega are just constants. Just treat them like they're numbers. Even if you don't like them, they're just numbers. If this were a math class, could you take the derivative of that with respect to t? And indeed, this is just like the first exercise or something on homework too. Whether you've done it or not, if you haven't done it, this will help you a lot. And if you have done it, then that's kind of what I'm talking about right here. So I'm just going to pause for a second for anybody who wants to put in the chat or say, I guess the chat is better so we don't distract other people, but I want cool. Yeah, good. All right, I see something in the direct chat. Well, I'm just going to respond. I'm going to shut up for a second. Yeah, if you just want to, I don't care if it's public or private. If it's private, just give me a moment to respond. But I think a moment to think is probably good for everybody too, or to catch up. So, and this isn't a context. We are in a context, but even if you've lost me or you're getting frustrated or bored, we could pause for a second. Like this is a fresh question. Even if you don't, like, even if you've lost the thread on why I'm asking it, it's good practice. We have x equals x naught cosine omega t. Trust me again that x naught and omega are just numbers. They're just constants. So the question on the table is, what is dx dt? I've gotten some things in the private chat, so I'm going to shut up for a second in response to them. Take your time, everybody. Hold on. Awesome. Oh, cool. That's cool. Maybe I should even, that's cool. I'm just going to respond one at a time. I'm not going to say right or wrong yet so that everybody can think, but. All right, go on. Does anybody, I really mean this. If nothing else, just to keep you guys awake for your own sake. Like, it'd be great if anybody, even if you think you already see the right answer in the chat, like there's no harm or foul in putting in the right answer yourself. Even the attempt to type it out, by the way, even if you think you're copying from someone else, like, and you know whether you're copying or not, but even typing it out is like good, just keeps the brain alive and everything. So if anybody wants to put what they, and also, by the way, you can totally write in the direct chat, sorry, what's the question or something like that? Like, you know what I mean? This is another come together. This is just like, let's like stay on the beam here kind of moment. And I get how hard it is to pay attention to a Zoom for 2.5 hours or whatever, for almost 3 hours. It's torture, but it's even more torture if you're not sort of invested, right? Or those of you who are still hanging around. And I'm not looking at who, you know what I'm saying, but just like, if you're going to get anything out of this, it's easier to try to follow along. So I just want one more minute. If the question is, what's the, and this, but this totally also is, I'm in effect, I'm asking the first question of homework 2. Homework 2 looks like this for a while. I'm just saying, if you have the function x equals x naught cosine omega t, if you know x naught and omega are constants, what's the x dt? I am going to say that the people that put in the direct chat that they think the answer has to involve sine, they're totally correct. I am going to say now, because I'm going to move on, but maybe you guys will try the next derivative. I am going to say that I totally agree with Caleb. He is right, but just because he said it doesn't necessarily mean that it was, but he is totally right. I do, and that's great. And everybody should get points. And the 2 people who put in the direct chat, like, you should put that for points as well. I don't care that it's private. I mean, I care, but like, it doesn't change the fact. But so, yeah, I think the answer is this. I do agree. And I think I hear my son. Oh, and I'm going to write it my way though. Like, well, yeah, all right, I'm going to do it. Okay, I'm going to say this. This is exactly what Caleb wrote. This is the right way to think about it. What Caleb did in the chat is he said, okay, the derivative of cosine is negative sine. And then he did chain rule. So because he's doing a function of a function. So he's saying the outer function is cosine, the derivative of that is negative sine, but it's a function of a function, meaning it's not cosine of t, it's a function of omega t. So then he took the derivative of that inner function. The derivative of omega t is omega. So he multiplied his whole answer by that inner derivative. That's what it means to be chain rule. Okay, that's what he got, and it's totally right. Now I'm going to clean it up a little bit, or I'm going to write it the way of physics. I'm going to gather all the constants in an order that I might want you to get used to. The way physicists would write a thing like this is they would write it like this. Totally equivalent, like his answer is 100% correct. But we have sort of a tradition or a style in physics where when we can, we try to collect all constants together and keep them isolated or separated as best as we can, usually at the beginning from the variable, which we like to have sort of as clearly as we can as an argument of the function. So this is the first derivative. Again, this is trigonometric derivative, which is sort of a memorizer, and chain rule. I can review those things on the side with anybody, but right now I'm just reminding you that is how we got it. It's the derivative of cosine is negative sine, and we had to do chain rule to do this. But now we're not done or anything. And I apologize to those of you who this is like pulling teeth, but we're not done. We now have to differentiate again. Why? Because our original differential equation had a second, had a second derivative in it. So we differentiate again. And we're going to do that. I don't know. I'm going to pause again. If anybody else besides Caleb or the 2 private chat people whose names will remain private, anybody want to try? And I totally get, and I'm not saying this to disparage, like, obviously I think it's clear that Caleb will get this one right, and that's cool. But does anybody else want to take a moment to try to take the derivative of the thing we just got above, like the derivative of negative x naught omega sine omega t? And I know things are looking funky maybe, but again, remember, the variable is t. Everything else that you see is in effect just a number. So I would say that, again, it's a trig derivative and it's chain rule. Does anybody else, and I won't wait forever, but does anybody want to take a stab even privately at the, by the way, the other thing you can do, because it also would
You want me not to put it in the chat?
Yeah, if you don't mind, or you can put it in the private chat if you don't mind. And it's not, it's a compliment, you know. How about put it in the private chat just to not, because everybody's just going to assume you're going to be right and they're just going to fall.
No problem.
Okay, thank you. We'll get this guy eventually, folks. No, yeah, I appreciate that. And let me say to everybody too, hold on, let me just change the view so I can see what's going on here. I am pushing you all to try to do this, but also it totally counts as participate. Any one of you, okay, could write in the private chat also like, I am listening, but I am lost, or I'm listening, but I have no idea, or I stopped listening 20 minutes ago, whatever. I mean, for me, just to know where you know the old saying, all of you, like if you cannot find Madison Square Garden and you walk up and you call somebody and you're like, dude, I'm totally lost. I cannot find Madison Square Garden. What's the first thing? And anybody can answer this if you want, just to show me that you're paying attention. Even if you're lost in the math, you can answer this. If you call up someone randomly and say, and I mean randomly, like just add it, like right now, you call up someone that you trust and you say, dude, my Google Maps is down, my whatever Apple crap thing is down, whatever Waze is down, I cannot find Madison Square Garden. Can you help? What is the first thing? And anybody, you can answer this in the chat if you want. And this could include Caleb if he wants. What is the first thing that your friend is going to say to you on the phone if you call them up and say, I cannot find Madison Square Garden? And if they're not joking with you, I mean, they could say practice, but what would they say to you if you say, I'm lost, I cannot find Madison Square Garden? What are they going to say? Oh, look at the chat. Oh, wait. Oh, I'm seeing a lot in the chat now. That's awesome. Yes, that's awesome. Okay. First of all, I just saw like 85 math things in the chat. So clearly this is working. But yes, what Catherine, so I'm going to read backwards. Thank you, Catherine. First, again, thank you, Caleb, definitely for being so respectful of both the math and the class. But thank you, Catherine, because yes, and that's so like, right? If I say something, I'm lost, where's Madison Square Garden? If it's a friend of mine who cares, the first thing they're going to say is, where the fuck are you right now? Like, and then they'll help me navigate. But if they don't know where I am right now, it doesn't matter how well they know Madison Square Garden. It doesn't matter if they're standing in the middle of Madison Square Garden giving a freaking concert. They can't help me unless they know where I am, right? And it's totally like that in school, and we forget that all the time. Like, as long as you trust me that I'm not out to get you, like, for me to help any and all of you at any time, what I need to know is where you're at. And there's no shame in it. It could be a different place every moment. But if I don't know where you're at, I can't get you to me no matter what, right? So now, but now I really do. So you're allowed in the chat to say, honestly, I lost you 20 minutes ago. It doesn't mean I'm going to grind the whole class. Like, I might not be able to do anything about that because there's 27 other people. But if 26 people write me that, if 26 people write me, I lost you 20 minutes ago. Well, I know I did something really boring 20 minutes ago or something, or confusing, and I better go back, et cetera, et cetera. But all right, it looks like there's a lot of math in the chat, so that's great. But as long as I'm ranting about math, let me also say the flip side of all of that too, and I kind of try to say this in that sheet, what to do when you don't, how to know what to do when you don't know what to do. The flip side is the one thing that science students say all the time, and scientists, people that are legitimately struggling with legitimately hard material, which all of you are doing in this program, and especially in COVID, the thing that always happens to people in the middle of homework or in the middle of a test, when they're good people and they're trying hard, what always happens is this moment, not always, but what often happens is this moment where a person goes, I have no freaking idea, right? And I mean, I've experienced that countless times. Taking an exam, like I'll be like, I don't even know what the heck you're asking me. I have no idea what this question's about, or I have no idea what the professor's been talking about for 15 minutes. Like, that's that feeling. And then usually it leads to stress or giving up or hatred or something, right? When you start not knowing what's going on, it's really easy to go, I have no idea what's going on. But I'm here to tell you all that that's actually the lie, right? That's the lie. That's the panic talking. We never have no idea what's going on. The minute we say we have no idea what's going on, it's usually because we're just starting to get a sort of clear idea that we've lost something. And it bothers us so much that we drop everything, right? The minute you start feeling, I have no idea what's going on, the most important thing you can do is go back, see, when was the last time I had an idea what was going on? What was the last place I understood what was going on? Go back there and then see exactly where you dropped the thread, and like actually try to isolate the idea that you don't know. And the minute you can do that, you're on the path, either to getting help from me or from yourself, right? But like, that's why I'm just like desperate not to get blank nothings from people, because then I know we've given up. But okay, so I'm glad I've got some math in the chat here. I'm looking at the math in the chat here. I totally got an answer from Caleb. I appreciate. I'm not even going to say if it's right or wrong, but I appreciate. Oh, I got something in the public chat from Catherine. Awesome. Awesome. Okay, and private chat. Okay. Awesome. Now I've learned a lot. Most people put in the direct chat. Catherine had the guts to put in the public chat, and Caleb would have, but I asked him not to. I totally appreciate that. I think as time goes on, the more we can have the guts to go in the public chat, the better, but it's great. Now, and here's the deal. What everybody, but there's a bunch in the private chat. Should I? All right, wait, do I want to? Actually, let me just quickly respond. Hold on, bear with me. But again, if you put it in private or public, you can totally submit this to the portal that says for right or for wrong, 75 points. Any one of you that put anything here, public or private, right or wrong, screenshot it, put it in at 75 points. And I am serious about that. Oh, wait.
You're in the public chat, just so you know, Professor.
Yeah, that one, yes, thank you. That one was actually meant for the good call, but that one actually was meant for the public chat, kind of to,
Okay.
but yeah, no, good call. Thank you. Oh, okay. Wait, but you're right, but I am still also responding to private chat, so just bear with me for a second. I'm just going in order. Wait, there's one more. I didn't. If okay. I'm about to go over. I think I've responded to all of them. Oh, okay, cool. All right. So there were a lot of answers in the private chat. There were answers in the public chat. One honest person actually, okay, well, so I'm going to do it. And some of the answers were exactly right. Many of them were close, but not right. So I did write in the public chat two things. I did mean to write them, but they might've been cryptic. I did say, watch the negative sign. And then I said, watch the double chain rule. I regretted that immediately. I don't regret saying it publicly, but I take back the phrase double chain rule. What I really mean to say there is watch the fact that we are taking a second derivative here. So we're going to do the chain rule again. So whatever results were produced by the chain rule the first time in the first derivative will occur again here. I don't mean to say that there's some fancy double chain rule or anything like that. But so what I am saying is, and a couple people asked me in chat, like, well, I know how to take a first derivative, but how do you take a second derivative? That's a fair question, by the way. That's also a very honest question. Especially if it is an honest question. Let me say to everybody, if you know how to take and it's not obvious, you might think that it is, those of you who know the answer, but if you know how to take a first derivative, then taking a second derivative just literally does mean taking a derivative of whatever result you just got. Like it means doing the exact same thing again, which is not obvious, really. There could have been some other rule, like it could have been the case, something else could have been the case. But
I
right.
have a question.
Yes.
So if you take in the derivative the second time, since it's negative already, it's gonna be negative twice. So don't two negative signs become positive?
That is a great, perfect question. That's an awesome. And by the way, who was that? Juanita? Wait, who was that actually? Sorry.
Yeah.
Oh, Juanita. Okay. Yes. So two negatives do become positive. That is true. And yes, if the second time we got another negative, then it would make the first negative vanish. And in a lot of the answers in the private chat, a lot of people said that. But here's the catch. So your logic is perfectly right. Here's the annoying catch, though, is that it just happens to be the case that when we take the derivative of cosine, we do get negative sine. But when we take the derivative of sine, we don't get negative cosine. We just get cosine. Like, and that I'm not sure if I can prove that right in this moment. But that is a math thing. But and it's a weird, surprising thing. But the derivative of sine is just cosine, whereas the derivative of cosine is negative sine. So your logic is totally right. But when I go now to take this second derivative and I take the derivative of sine, I'm not actually going to add another negative sign because the derivative of sine doesn't work that way. It doesn't actually produce. So again, so logically, yes, if there were a second negative sign here, it would cancel out the first one. But we actually don't get a second negative sign here. The derivative of sine is just cosine. So that x is just, that negative is just going to sit there. I don't know if that helped or if that's clear. Well,
Yes, that's clear.
okay, all right, thanks. But that's a great question. And again, and this is the thing I got to say, and I'm sorry to go, so she had the guts to ask that, right? What a lot of you in direct chat can't know until Juanita just asked that is like, I think 4 people in direct chat all had something like that. Like she's totally not alone. It's totally worth raising that. But not one of you in direct chat could ever know that that's the case until someone like busts through. So I'm just saying there's like at least 5 people in the room that I think benefited from hearing that. So thank you. But now then we do, but then the other thing is someone asked in direct chat, like, what do we do about second derivatives? Well, you really do just do the derivative all over again. So I really am doing the derivative of that whole function. So the omega will come out again, like I'm doing chain rule again. So I still have to bring that omega out just like Caleb originally did back in the day. So I have this long, complicated looking answer, but if I clean it up a little bit, since multiplication is commutative, like it doesn't matter what order you multiply things in, you still get the same answer. So I can bring that second omega to the front. And I get this. So this is what I would say is the final answer, which some of you totally had and totally get right. And yay. And maybe eventually I'll put in a portal for right answers also, but I don't think so. But a lot of you put an answer at all, so you all get points. So there's this. Now I'm going to go one step further. So this is the answer, okay? What time is it? 3:15. All this, and I still haven't proven anything. And let's also remember that I talk a lot, obviously, and I'm trying to explain a lot. Like if I were to ever ask a question like this on an exam, I don't expect you to have to write things for an hour and 75 minutes, right? I'm trying to break this down for everybody. But the actual steps that we've done here so far is just a couple of pages worth. And now we're almost there. I now have the second derivative of x with respect to t is this expression on the right-hand side. I'm going to do one more step. I'm going to, because again, like this is just a bunch of multiplication. It's x naught, but really it's -1 times x naught times omega squared times cosine of and so I could do this if I want, or I could even do this if that makes it easier to see. But whatever it is, it's multiplication. So on the next page, I'm going to say, okay, this is just a recopy. I'm just recopying. But now I'm going to say multiplication is commutative. Oops, sorry. And now so all I did was like scramble around the x naught and the omega squared. They're both constants. They are both just numbers. I just rearranged their positions. But now, why did I do that? Now note that entire thing in the red brackets, that entire sequence x naught cosine omega t, that's just our original conjecture for x. This is the key step, and this is a step that people often don't see until they get used to it or they forget or something. This is the key. Oh, sorry, I'm flying. This is the key step. Sorry. Okay. Is to recognize that our original x is sitting there on the right side of the function. Or put another way, like we originally were hoping, we picked cosine because when you take the cosine, when you take the derivative of cosine, you get negative sine. Then when you take the derivative of negative sine, you get, strangely, surprisingly, as per Juanita's question, when you take the derivative of negative sine, you get negative cosine. So when you take two derivatives of cosine, you get back the original function times a negative. And that's exactly what we wanted here. We wanted to get back our original function times a negative and then times some kind of constant. That's what seems to be happening. We did get, in other words, we did get back our original x. Our original x is sitting there, x naught cosine omega t. In other words, yeah. Hold on. I see there's something in the chat. I'll see that in 1 second. Okay, I see there's something in the chat. Oh no. Wait, wait. Oh, okay. Wait, no, wait. It's the omega sine on this side. So wait, it's the omega sine. One second. So I'm just responding to a couple of things. People are really using the direct chat the way that I think is great. I totally appreciate. So bear with me, everybody, for a second. But I'm saying we're just about done with a very big thing. And yes, I know you've seen it in lab, but hopefully it's coming together with lab. But let me just respond to these direct chats for a second. I'm pausing just for a second because there is dialogue happening in the private chat. So some helpful things are happening in the private chat. And some people are even admitting certain things that are confusing, which I do want to straighten out. And I don't, and I want to give people a chance to think. Anybody who is trying to think right now should be rewarded. So I'm going to slowly, so I'm not sure if I've answered the private chat question properly or not. I'm going to slowly keep talking, but
I have a real quick question.
yeah, okay, yeah.
Actually, first of all, we're not supposed to be thinking about something you've written on the paper right now, right?
Right. You're not supposed to be doing it.
Okay. The question I have is sort of like, all right, so like all these derivatives and all the rules and all that in the class, which I hope you remember, like such as like real analysis. Do we re-go over all of that just in a more rigorous and comprehensive way so that like you don't kind of forget how it makes sense a little bit? Like, I kind of forget how the chain rule makes sense. I know how to do it every time. I could kind of remind myself, but it's not just at the front of my mind whenever I want it, you know?
Totally. That's a great question. All right. And that's a perfect example. I'm totally glad you're raising that. I would like to think that pretty much anything, not always right away, but almost anything we use enough, I want to say, yes, I will. We should re-explain it so that it is like in the front of your mind and fair and clear. And the chain rule is a perfect example. You're right. I have not actually given any real good logic for the chain rule yet in this class. I totally will, especially now that you raise that. And I think, in fact, I will today in 2 minutes. I don't know if it'll totally, do the whole trick. I may have to say more about it later. But yes, no, you're right. Anytime there's a thing that you sort of hazily remember, but it's not in the front of your mind, or you know it's true, but you don't really believe why it's true or remember, it is, I do consider it my responsibility to at least try to break it down. So yes, I will with the chain rule in 2 minutes. And if I get to a point where I'm like, now this is going to get too much, let's talk privately, I will. But the chain rule, yes, I'll give you at least an argument for it in a moment. Oh, okay, right now I will, because the person in the private chat just totally, all right, so yes, that's great. Let me say something about the chain rule to everybody, because the chain rule is kind of out of nowhere, I agree. But also let me again say, someone in the private chat just sort of said something they didn't understand. Then I tried to give an answer. I didn't know if my answer helped or not, because I wasn't like totally sure I was answering the question. But then they said in the private chat, I understand now, that I'm totally going to make a portal for doing that. Like, again, because now I know I can move on, right? And I can answer Caleb's question now. Like, that is super helpful to everybody. And it's amazing how people in life do not do that a lot. They just like leave everybody hanging all the time. Or they ask a question, why a lot of people won't do that. So I'm praising the person who's in the private chat, even though it's private praise. A lot of people won't do that. They'll, in life and in classes, they'll ask a question and then kind of like start phasing out as you're answering. You can see their eyes glazing over and they're sort of not paying attention. And then they'll like walk away when you're done and you never even know if you've answered the question for them or not. And what that proves when people do that is that they never cared about the answer in the first place. They just wanted to hear themselves asking that question, right? They just wanted to show everybody else like something, which pisses me off. So I appreciate it when that doesn't happen. Now, Caleb's question is clearly not that. Oh, wait, hang on. I am going to answer Caleb's question. Let's look at the time.
I want to say something, Professor, that whole asking a question thing, that is true a lot, but as someone who's conscious of my ability to sort of phrase what I mean, sometimes I do that as well when I understand that I'm just not, I don't have the computational brain at that moment to say what I actually mean, because for maybe I've been focusing for too long. So I do that sometimes for that reason as well.
Oh, wait, wait, you mean you'll ask, I'm totally psyched that you're bringing
If I have to ask my professor something like 5 times and I'm conscious of how I'm saying it, if I realize that my words aren't depicting the exact thing that I mean because I understand rigor to a certain level now, I'll be like, all right, I'll do this another time. I'm not getting it right now because I understand if it's my fault, then I'm not there's no point in hitting your head on a problem over and over again at that moment. Go back to it later. You know what I mean?
Right. Oh, that's totally fair. But you'll do, no, that's totally fair. But you'll actually admit that. You're saying you'll be like, all right, this isn't actually working.
Oh yeah, most of the time, yeah, you're right. I'll usually say, you know what, I'm not phrasing it right now. I usually say that.
Right. No, and in fact, I think you even did something like that in the second day or the first day of the class. No, and I totally appreciate that. That's completely cool. That's a high level of self-awareness, especially like what you just said, that you even know that sometimes the way you're just doing the question is just not going to help in that moment for you or the other guy. For you to be able to like cut bait and say, all right, yeah, I'm not getting it now, but another time, that's totally respectful. Like everybody can walk away with no shame there. No, I don't, and I totally believe you do. The thing I just can't stand is when people ask questions and then they just like walk out which I do see, I see no evidence that you would do.
I get what you mean. Yeah, I get what you mean.
Right. All right, cool. And even that, you see, folks, how he said, I get what you mean. You see, all right, anyway, this can all just be a big spiritual journey. All right, but I want to answer his question about the chain rule. That's very fair because it is kind of an obscure rule, but I think I can make a little bit of sense out of it. Yeah, all right, I think I'll say one quick thing about it right now before I lose the thread, but then I do want to finish this thing. One thing about the chain rule. This is not a proof what I'm about to do. I mean, of course, I do have to be careful, right? I mean, this is a physics class, not a math class. If I fully rigorously redo everything perfectly, then you guys are all back in like a different class and we never get to the physics material, blah, blah. But what I can do sometimes, hopefully, is just a way of thinking about a math thing that can come into more focus now that you have a physics perspective. And one way I find, one thing that I do that makes the math make sense to me is taking the notation super seriously. Like the way I tried to answer that question before, whether it worked for anybody or not, but when I tried to break down like d2x dt squared and show why the 2's are in that place, that if you actually start believing that the notation actually is not an accident or a coincidence, that someone did try to think it through and make the notation work, like it doesn't always solve all the problems, but it helps to believe that because it helps you know where to search for solutions. So in the case of the chain rule, think of it this way. Okay, the chain rule comes up. So this is to everybody now. Either if you have no idea what the chain rule is, this might help a little bit, assuming you sort of remember what derivatives are. Or if you do know the chain rule, but you've never like really known why you were doing it or what, or like it just seemed like a raw memorizer to you and you want some perspective on it, this might help. This is the way I think of it. The chain rule comes up whenever we have a function of a function, right? Whenever like we have some box where you put a number in, call it X, and the box will pop out a different number, call it Y, you know, such as Y equals MX plus B, or Y equals AX squared plus BX plus C, whatever. Like you have some function where Y is the output and X is the input. Then if you take the output from Y and you put it in a new box. You put it in a new function, call it z, like I'm just arbitrarily calling it z, so that the output of the first box is the input of the second box, right? So z is a function of y, which in turn is a function of x. If like that's the situation that prompts the chain rule, okay? And what I'm about to do is tell you how you take derivatives in a case like that. Like the question is, how do you take the derivative of a function of a function? Like that is what the chain rule is meant to address. So I'm just gonna write that, hold on a second. So how do we take the derivative of a function of a function? Okay, and the answer is almost shockingly simple, not easy, but simple. The answer, assuming this page, assuming y is a function of x. Oh, I'm sorry. I mean, I guess technically, I'm sorry. If you were in a math class, I might actually say that z is I probably should have said z is some other function. Like I can't use the word f twice, I guess, technically, because I don't mean to say that they're the same function. I mean, say y is some function of x and z is some other different function of y, right? So like, you know, maybe you plug in x into y equals mx plus b, and then you get out some number, and then you plug that into like z equals ay squared plus b or something, right? So you have two different functions and they're built one on top of the other. How do we take the derivative of the whole mess? Well, the answer, math says, is this. This statement right here is the chain rule. And if you think about it, it really actually makes sense. It's called the chain because you can just keep doing it and doing it and doing it. Every time you build a function on top of a function on top of a function, you can always do it. But what is the it that I'm saying? The it is what we're just saying is the derivative of the outer with respect, the derivative of the way outer, the derivative of z, the rate at which z changes as a function of x is simply the rate at which z changes with respect to y, i.e. the derivative of the outer function, times the derivative of the inner function times the rate at which y changes with respect to x. We're saying dz we're saying dz dx, or in other words, rate of z with respect to x is simply equal to dz dy times dy dx, because derivatives actually are fractions, like I was saying before. These are single derivatives now, like not, and so it's kind of like cross multiplication. Like if you just you can see that those dy's like cancel out to give you dz dx. So, and literally what this means is derivative of outer times derivative of inner. That's all we're saying, and all we're doing when we do the chain rule. We're saying if you have a function of a function, then take the derivative of the outer function and then multiply it by the derivative of the inner function. So in our case with the trig thing here, we had cosine of omega t. So first we do derivative of cosine, we get negative sine. And then we look on the inside. We didn't just have cosine of t, we had cosine of this inner function, omega times t. So we take the derivative of that, omega, and literally multiply the outer by the inner, because dz dy times dy dx, if you just cross out those dy's, gives us dz dx. That's the way I think of the chain rule, that it's literally like multiplying fractions. I don't know if that helps or not. It's not a proof. It's just a way to think about why it sort of is not shocking that the chain rule works. Hopefully that helps a little bit. I'm not even going to find out though. I'm going to go back now to where we're,
That helped. It helped.
okay.
This is the second time this class I had one of those. You hear it 50 times. It makes sense.
All right, cool. Excellent. No, I'm glad. And I thank you for saying it helps. So you totally did just prove the other point too. All right, cool. And that's a great question. I'm sure there's 85 other people that needed that, or actually I always like writing it anyway. Okay, no, thank you. All right, cool. So now back to what we're almost done, back to this. I've just about, 3 days later, just about made myself feel as though I've just about proven something. I've certainly accomplished something. Well, I mean, we've accomplished something. Like we were looking for a function x such that when we differentiate it twice, we get back itself times some constant times the negative. Now we sure as heck got that. We show that with cosine of omega, x naught times cosine times omega t, when you differentiate it twice, you get negative times omega squared times x naught cosine omega t. So we got back x times some constant times negative. Now this is all English though. Let me remind you, like what were we actually trying, specifically the function we were looking for, trying to solve. Hold on. Save, so, okay. Come. How do we? Here we go. Okay. So to be explicit, remember we were trying to solve d2x dt squared equals negative k over mx. We wanted an x such that when we differentiated twice, we got back itself times a negative sign times some constant. The constant we were saying was k over m. We made a big point of saying like k is a constant, m's a constant, so k over m is some constant. We could call it whatever we want. We could call it C3. We could call it C. Right. Wait, I'm seeing something in the direct chat. Well, I'm just responding to something in the direct chat. Okay, there's a good question, direct chat, which I just tried to answer. I may try to answer more publicly in a second, but I'm just going to go on for a second. We were trying to solve that differential equation that had the K and the M in it. We made a big deal that K over M, K and M are each constants. Together they make one constant. We can call that constant whatever we want. Changing its name doesn't change what it is, right? And then we got X equal, we said that if we use X equals X naught cosine omega t, then that seems to work. It seems to solve the differential equation in that when I differentiate it twice, I get back d2x over dt squared equals negative omega squared x. And omega squared is a constant, just like K over M is a constant. In other words, we did end up finding something that had a different name for our constant, but we took great pains at the beginning of the discussion to say, we don't care what name we use to call our constant, like it's just a constant. So in other words, we were saying, even if we get that constant back under a different name, whether it's K over M or call it A or something, as long as it's just a constant, then we've done our work. So in a long way, what I'm trying to say is, what this means is, it means we've actually just learned two things. It's not what I meant to do. Oh, I guess it is what I meant. Yeah, it means, in effect, we just learned two things. One, we learned a solution to our differential equation. Like, it does mean that we did verify that our attempted function did work, and from now on will be the answer that we're looking for in order to bring this all back home and get an answer. It does establish that the solution we were looking for works, but also it establishes something. It tells us what that omega thing was that we just made up in the first place. We just made up omega, knowing there had to be some kind of constant there. We didn't know what it would be or what it would mean physically. We just knew there had to be some constant measured in radians per second. We just gave it a name called omega. And then omega ended up getting squared and being in our final finding. What I'm saying now is this whole game seems to work as long as omega squared is just another name for K over M. Right, that's what we've really learned here. We've learned two things. We've learned that this works and is the answer we're looking for. And we've learned what we mean by omega, that wiggle rate of the cosine curves. Let me write down what I'm saying. I'm saying this. And this is where we're going to end, but and it means I'm lying because we're not getting, well, we in effect got to homework 2 somewhat today. And if you look at homework 2, you'll see that we've done the first like 3 exercises of it in this class, but we're still going to stop in 10 minutes. We're saying two things. And the first one is, they're both so important. I mean, they are a conclusion. And with 7 minutes left, what I'm going to just do is just show you how to use these conclusions to plug in numbers and get a final numerical answer to question 9 of homework 1, so we could put homework 1 to bed forever. I mean, not, you can still hand it in and all that, but to finally put to rest all this work. The important finding is, first of all, we have solved the differential equation. To this differential equation, Hooke's law, to this differential equation, the solution is this cosine function. Number 2, we're saying this cosine function does solve it. It is the answer if and only if omega squared is just another name for the combination of constants K and M, spring stiffness over mass. In other words, to show you how this works, in other words, you know, sorry, this is so important. I'm going to write it on the next. Well, no, I can't. Okay, we have 6 minutes left. This is super important. I know it's the end of class. If you've been spacing out, and forgive me, I'm not going to do any questions for 6 minutes. This is a big deal. And I think you have got, well, I believe you've gotten it in lab now, but let me say it my way. And let me try to put this all together because it is a conclusion. First of all, I'm saying now, from now on, anything that's going back and forth, any system that's going back and forth in the manner of a mass on a spring, any system that can be shown to be mathematically equivalent to a mass on a spring. So that does mean your simple pendulum that you did in lab 2, or I mean your planar pendulum that you did in lab 2. It means other things that are going to come up in this class. Anything that can be shown to mathematically be equivalent to a mass on a spring can have its space predicted in time according to this position function. Like, this is the solution that we use from here on in. X equals x naught cosine omega t. Technically, that omega, that wiggle rate, that rate at which the rate at which the system cycles per unit time, we call that a frequency, or technically an angular. And I know where I gather Professor Wu has said all this, but again, this is just now to put it together. That omega is called angular frequency. It's the frequency with which the system undergoes cycles. We measure them in angles because an angle is a portion or a fraction or a section of a circle, right? Like a 90-degree angle, whether you call it 90 degrees or you call it pi over 2 radians, what does it really just mean? It means a fourth of a circle. And anything that is cyclical can be thought of as circular, right? So angles are just portions of circles. In effect, angles are portions of cycles. So omega is angular frequency, just meaning how quickly the thing cycles back and forth. X naught is the initial position, right? The initial stretch from equilibrium, and thereby according to energy conservation, is the maximum stretch that the thing will ever undergo. So x naught, which is both the initial position and generally the maximum displacement from equilibrium, we call the amplitude. So this is just vocabulary now. All right, from now on, like x naught is the amplitude, omega is the angular frequency, and anything that is described by that differential equation is solved by this cosine function. Again, the differential equation is Hooke's law and it's mathematically descriptive. But if you want a plug-in of you tell me the time, I tell you the position, this is it, this cosine thing, okay? And it has amplitude and angular frequency. What I'm going to say further with 3 minutes is for anything that now obeys this, we call harmonic motion, or I should say harmonic oscillation. I'm sorry, either one, but it's not just oscillation. Anything going back and forth is oscillation, but anything going back and forth according to these strict details, anything going back and forth according to this math is called harmonic oscillation. And harmonic specifically means that the frequency, the wiggle rate, the cycling rate is a constant, like a number that doesn't change. Omega is a number that doesn't change, and a number that doesn't change and that stays constant independently of the amplitude. Notice, and this is where I'm going to take one more page. I hope you got this. I know there's 2 minutes. Notice that we solved, by solving this differential equation, we not just got x naught cosine omega t, but we actually figured out what omega is. In order for this all to work, omega is the square root of k over m. It's determined by the physical parameters of the system. It doesn't have an x naught in it, is what I'm saying. Omega has nothing to do with x naught. The wiggle rate will be the wiggle rate regardless of how far out you pulled the spring initially. That is the meaning of the term harmonic. Harmonic means a frequency that is constant and independent of amplitude. Okay, hopefully you can see that at the bottom of the page. There's one more thing so that's the big takeaway, is that this is the position function for harmonic oscillation. This is what we mean by harmonic oscillation. This is how the constants are related in harmonic oscillation, such that, with 1 minute left, just to wrap this all up, such that, to go back to the original thing, and bear with me if I go 30 seconds over, but just to wrap this up, back to question 9, like we've answered it now in general. The answer is x equals x naught cosine omega t. But if we actually want a numerical answer to what was actually asked in the homework, they said, given, and again, this is the last thing I'm writing, just this page. And if you have to go right now, go, no harm, no foul, but I just want to finish this so it's all finished. Mass equals 0.3, x naught equals 0.15, k equals 200 newtons per meter. Was there anything else? I think that was it. And we wanted to know, and t equals 1. We wanted to know what is x. This was the very last question on the first homework. What I'm saying is x equals I'm going to have to go to the next page. No, I can do this. Well. Now, you have to do this on a calculator. Your calculator, this is where we're ending, right here. I apologize for going over. Your calculator must be in radian mode. This all assumes radian, but if you plug these numbers into your calculator in radian mode, I believe what you get is 0.116 meters. That's the answer to the very last question of homework 1. We will directly go to homework 2 the next time. But again, if you've done homework 2, you'll see that we've already talked about some of it. I owe 10 of you homework 2. I apologize. That's all I've got. You could totally go if you have. I'm going to hang out for 7 minutes or whatever if there's any questions, but that's it. You've been very, very, very patient. And just do homework 3 if you're up to it. And if not, work on homework 2. And I'll see you tomorrow. But thank you very much. Thank you. Awesome. Thank you. Awesome. Yes. I'm just here just in case there's anything, but thank you. Awesome. Thank you.
Yeah, Professor.
See you. Awesome. Thank you.
Thank you, Professor. See you tomorrow.
Thank you. See you tomorrow. Yes, thank you very much. Awesome.
Thank you, Professor.
Thank you. Awesome. Thank you. Okay. Thank you. Oh, all right. So Matthew or Noelia, you guys good or question or you think Noelia, Matthew, good? You're good. Oh. So you got Matthew, Noelia, you guys good? You're good? Okay, so I'm gonna go. Thank you guys very much. Have a great everything in the world. Quark plus America. Yes, okay. Quark plus America. May the field be with you.